There we go. So make this full screen. Here we go. So making one of these salcs, which shows the orbitals interacting, is largely about making one molecular orbital that has the same symmetry by putting together the components. So we did some p orbitals inside of this cube with the hydrogens around the corners, and we showed how the p orbital in the central atom and those hydrogens have to be shaded in a self-consistent way. The resulting MO has the symmetry of the irreducible representation. Okay, so you just need to make the pluses and the minuses match up in a way that gives you T1U symmetry, for example. So we're going to do a little bit more of that today. We didn't quite finish our example of titanium tetrahydride. Let's just quickly, one time before we do that, revisit. In the case of methane, one of the things we did was to generate the reducible representation of the 4 hydrogen 1s orbitals. And how do you do that? Go ahead, Jordan. Yeah, so you go through all the operations in the character table and you ask, if I apply this operation, how many of these hydrogens move? If they move, they're going to go off the diagonal. They'll contribute the 0 to the trace of the matrix. We want to know the ones that don't move. Those contribute a 1 to the trace of the matrix. And you write that down underneath the table in each operation. So in the case of CH4, the do nothing operation, the E operation, all 4 stay put, and you get a 4. That says the reducible representation has a dimensionality of 4, right? C3 operation contains 1, the other 3 move, so you get a 1. All right, so you have to do that to get this reducible representation business. All right, so let's finish up here with titanium. Okay, so in the titanium, well, maybe I'll put the diagram back up there. Where did you go? Make sure I have it right. Oh, we also talked about the photoelectron spectrum of methane. What was special about the photoelectron spectrum of methane? Can you picture that spectrum? Go ahead, Margot.
They were not degenerate as we might expect. There were 2 peaks.
There are 2 peaks, right? And what does that say? It says there are 2 different kinds of electrons in methane. One that's lower and one that's higher. And the ratio of the peak intensities was 3 to 1. Not what you expect, right? Methane's got 4 CH bonds. They all look the same. Why are the electrons different? Well, it's because methane is using an S and a P to make those molecular orbitals. And when you ionize methane, the product can have 2 different kinds of configurations, S and P. Okay. So it's confusing. You see the 4 bonds, you see the 2 lines in the photoelectron spectrum. There's no issue. Okay, the molecular orbital description and the valence bond description of hybridization are 2 different angles. They're 2 different approaches to talk about the same thing. Okay, and it seems sort of contradictory, but it's not. All right, let's take a look again here at our diagram. Can you guys see this corner of the board? Not quite. Let's take a look at methane again, or titanium tetrahydride, right? Titanium, we're going to combine 4 p orbitals, 4 s, 3 b. This is A1, this is T1U, this is E, and T1U. Sorry, not U, just T1. I think it's T1. Is it T1? T2. T2. Sorry. Got octahedral in my head, I guess. All right. So notice 4p and 4s are above 3d. It's different than the electron configuration of the atom. Now we got to put 4 hydrogens up here. And where do those go? Below the transition metal. Got to remember that. 1, 2, 3, 4. And these guys have the same symmetry as orbitals on the metal. Anybody remember what they are? A1 plus T2. One way to figure that out is by asking, what kinds of orbitals do you think these hydrogens make a connection to? Okay, and it may be hard to visualize in tetrahedral. It's a little bit easier in some of the other symmetries. One, the 4s orbital, definitely going to make a connection with the 4s orbital. It's a sphere. You got a bunch of spheres around a sphere. They're definitely going to talk to each other. And then since we've done methane, we know that T2 is the other one. So one of these guys, the E, is non-bonding. Right? T2 and T2. We're going to make a connection there. We're going to make a connection here. This is the 1 T2. This is the 2 T2. This guy, 4p, also makes a connection in here. 3 T2. And then we have the A1. 1A1. 2A1. Okay. And most of the time, we're really going to be interested in talking about what's going on with the d orbitals. And I'll tell you, we're going to treat these things here like they're the d orbitals. In reality, these are molecular orbitals. And in this case, they happen to be only localized on titanium. But here, they're localized on titanium and the ligands. And there's 2 different contributing functions. Okay, so this orbital is more complicated than just a d orbital, but we're going to talk about it like it's a d orbital. Okay, and so these things right here, we said, are the frontier orbitals. They're the ones we care about. Titanium has 4 electrons. Hydrogens have 4 electrons. Put them together, you have 8. 1, 2, 3, 4, 5, 6, 7, 8. Where are the electrons in titanium tetrahydride? Forget about this diagram for a second. 4 electrons from the titanium, 4 electrons from the hydrogens. They go together. Titanium is on the left-hand side of the transition metal series. It's kind of like potassium. It's electropositive. So where are the electrons in titanium tetrahydride? Yeah, they're sort of toward the hydrogen. Hydrogen is somewhat electropositive too. So titanium tetrahydride is a pretty good reducing agent. It's a ferocious reducing agent. It will reduce dinitrogen. It will certainly reduce dioxygen. It's a flame if you expose it to air.
When you're asking us about the where you're asking about where the electron density is going to be, we're talking about dense role, right? You're referring to like
Well, I'm referring to the electronegativity difference. Right?
So,
And so, when you think about that molecule, you don't really have a lot of choices, right? Either on the hydrogens or shared between the hydrogens and titanium, or they're on the titanium. And this is a question of degrees, right? So you need to think about the electronegativity to answer that question. If this were titanium tetrafluoride, of course, no brainer. Fluoride is a whopping, it's very hungry for electrons. Titanium is electropositive, so no problem, gives them up. Titanium and hydrogen, they're kind of shared, sort of covalent. So now look at the diagram. You want to ask a question?
Yeah, about the two T2 orbitals, are they more anti-bonding between 3D and 1s, or are they more bonding between 4p and 1s?
When you have a situation like this, where you have three levels, there's one way down here that's really bonding, there's one way up here, it's really anti-bonding. The one in the middle is kind of non-bonding. Okay.
But it's an interaction that involves both the 4p and the 3p orbitals.
And the hydrogen 4s. It's linear combinations of all of them. We'll write out some wave functions in just a second, okay? So these are the electrons in titanium tetrahydride. I just asked you, where are the electrons in titanium tetrahydride? And you said, well, they're shared between the titanium and the hydrogen, or I said that. And what kind of MOs are these? They're bonding orbitals. What kind of character would you say they have?
S and P.
I would say a lot of S character from the hydrogens. And part of the reason I say that is they're close in energy to these, right? The nearest atomic orbital are these hydrogens. So these MOs have a lot of hydrogen character. These up here, they have a lot of titanium character. They don't have a lot of hydrogen character. This is mostly an empty orbital on titanium. Okay. This is mostly an empty p orbital on titanium. It has some p orbital character. It has some hydrogen 1s character, but it's a lot of titanium 3d. Okay, so you can think about these diagrams as perturbations of the atomic orbitals. If you start with two atomic orbitals that are about the same in energy and you split them, the product MOs are going to be mixtures of the two. But when they're really different, you're just like perturbing them a little bit. Okay, so these MOs down here look like hydrogen functions. All right. So let's draw some out again. We already did some of this stuff. Let's do okay. So which orbital is this one?
Like 1s or 4s.
And so what label would you give it here?
2A1.
2A1. This is the 2A1 orbital. And we're going to call this psi 2A1. This thing is going to be a linear combination. 1SH1 plus 1SH2 plus 1SH3 plus 1SH4. And it has the opposite sign. So we'll say minus coefficient 2 for titanium 4s. Okay, let's do another one. Which orbital is this one? So this is sort of a little bit confusing because in fact, this T2 orbital has some p orbital character in it. This is sort of like an incomplete molecular orbital because it does not contain any of the d characters. So I've only drawn a fraction of the interactions here. Okay. So in, one thing you could write here, let's do it like this. So in fact, as I said, this could be a component of 1T2, and it can also be a component of 2T2. Yeah.
Why have we drawn the one A1 orbital higher than the 1T2 orbital?
Well, so very good question. Things like this get very tricky. In general, if the orbitals are closer together, they will have a stronger interaction. Okay, but S's and P's and D's have different degrees of overlap. So you're sometimes stuck guessing what's the appropriate order, and you won't know. And I might have a different opinion than you, and you might have a different opinion than you, and maybe all three of us don't agree, and nobody's right. Okay, to really know these energies, you need a computer. We're going to do our best to guess. There are some rules. One is when they're closer in energy, they have a stronger interaction. Okay, so we have T2, we have T2, we have T2, and then A1 and A1. So which one goes lower? Well, because you have three T2 orbitals, this T2 set can be bonding with respect to both. Okay, so maybe the combination of bonding interactions with both pushes that lower than 1A1. That would be my intuition about how to think about it, and I could be wrong.
So,
But in general, even if you forget about this one, these two are closer in energy. And so I would expect that to be lower as a result.
okay. So it's different for methane, but it doesn't necessarily have to be consistent.
Well, in methane, there's a different situation. What's different about methane? There's something else. What's that?
There's no d orbitals.
There's no d orbitals, but there's something else.
Is it that, I mean, it's covalently bound, it's not a polarized bond. Would that affect energy levels?
There's something simpler than that. Well, the important thing here is we've got 4s and 3d here. In methane, what are our basis functions on carbon? 2s and 2p.
Because it's all the same energy shell, you can tell which one's lower.
That's
So
right.
we're gonna give an energy shell, so-
And which orbital within 2s and 2p is lower? 2s is lower. Okay, so now if 2s is the low one, then that's going to make the A1 interaction stronger. Okay, so closer energy, wider spacing, generally speaking. Okay. So let's just write out the wave function for this guy. We're going to call this one well, let's call it we'll call it 1T2. So this bonding combination here is going to be some coefficient times 1SH1 plus 1SH2 minus 1SH3 minus 1SH4. So the pluses and the minuses indicate the shading, right? And then we're going to give this a plus C2 4p orbital. Okay, so that's a bonding interaction. So I've written a plus. So you're going to get positive interaction with 1 and 2 here. And then these two on the bottom have the opposite sign. So this is an incomplete description. In the simplest one down here, the 1T2 orbital would also contain what? Some 3D character, right? So you could in fact add plus C3 titanium 3D. Right. Plus titanium 3D. Squared. Did I get that right, or is it not x squared minus y squared and dz squared? No, this is correct, isn't it? T1u. This is not right. Sorry. Those are the d orbitals. So out of practice. 3d xy plus 3d x. All right, so let's draw those things out a little bit more so you understand where we're coming from with that. So how do you get a positive interaction with the d orbitals? This is the same exercise that I was telling you about earlier. So let's take the T2 symmetry d orbitals here. So let's say this is Z, X, and Y. And what orbital is that? This is in the plane of the blackboard, same as the plane of the blackboard. So the two axes that are also in the plane are Z and Y. So this is a DYZ orbital. Now we've got our 4 hydrogen 1s's here. How do we make those overlap with that thing? Ethan?
Stagger the shading of the 1s orbitals and hydrogens.
Okay. Which is that one? Shaded or unshaded? Shaded. How about this one? Unshaded. So this combination of hydrogen 1s functions, which p orbital does it overlap with? Because p orbitals are also T1u symmetry. So let's forget about this d orbital for a second and just look at the 4 hydrogens. And remember that a p orbital has a nodal plane, right? You can see those 4 hydrogens also have a nodal plane, dividing them in half, right? The ones in the back are shaded and the ones in the front are not. So the p orbital that has that same nodal plane, which is the plane of the blackboard, is the one oriented along x. So this is the same symmetry as px. It's confusing because what I see when I look at that d orbital is that it sits in the nodal plane of the px orbital. That's confusing. I've been telling you, you can't have interaction. There's a plane here and it contains the other orbital. But in TD and in other symmetry situations, you're going to find the same thing. The symmetry is the same. Okay. They're not orthogonal to each other. They have the same symmetry. All right. Okay. So let's just draw this thing out quickly here. So what I'm going to do is I'm going to get rid of the x direction, eliminate the three-dimensional aspect of this thing. Now we're just going to look at z and y. Put those separately. So looking down this axis, upper left, lower right are shaded. This guy back here is shaded. And also in the back of the board, that one, the front of the board, and the front of the board. Okay? All right. Yes.
So if the TF orbital does bond with this unit of the same symmetry, is it a bond or?
So is this a pi bond or a sigma bond is the question, right?
Yeah.
How do we define pi and sigma?
Nodal planes, so how many nodal, pi bond will have two, one nodal plane.
One nodal
Delta
plane
will have two.
on the internuclear axis. That plane must contain both atoms that form the bond, or whichever atoms that are forming the bond. And there is a plane here, but the hydrogens are not on that plane, so it's not considered a pi bond.
The hydrogens are not on the same plane. Like when I look at this, I'm seeing the new element of the. So when I think of the nucleus, I think of it in the center of that.
Well, this nucleus is here, but what about the other one?
Well, for the p orbital, it's going to be, if you're saying it's going like along the x, right? Going on x, and the nodal plane of the node actually for the p orbital is in between the two lobes. So it's like on the same axis, but it's like I see the orbital of the lobe is blocking.
So when I say, but you must have both nuclei on this plane, the nodal plane. And these hydrogens do not have a nodal plane going through them. Okay, so first of all, a hydrogen will never make a pi bond because it doesn't have a node running through its nucleus. Can't make a pi bond with an s orbital. You can make a pi bond with a p orbital, you can make a pi bond with a d orbital or an f orbital. You cannot make a delta bond with a p orbital. Delta bonds require two nodal planes intersecting that the nuclei fall on. They have to share those same nodal planes. You can't do that with the p orbital.
Weird that I would know, I really like how we can make a pi bond, but then I could live in looking at how we can be receiving it.
Okay, so one last thing about this, and that's that this is still incorrect. So let me draw out psi 1t2 for a second here. So we're going to give this some coefficient, and we've chosen 3dyz on titanium here. And we're going to have another coefficient that's going to be 4px. And we're going to have another coefficient, 1h1 plus, 1s h2 minus 1s h3 minus 1s h. Okay. So this here says the all bonding combination of these guys, this is going to be the symmetry, or a way to write out 1t2. Now, let me ask you a question. Think about the coefficients in this MO for a second. Which coefficient is the largest? We're talking about the 1t2 orbital here, right? The lowest energy combination of these three components. or I guess more than 3 components. So C3 is going to be the largest, right? It's down by the hydrogens. And which one is going to be the smallest? 2, because PX starts highest, right? So C3 is going to be greater than C1, which is going to be greater than C2. All right. So, so now we're going to switch gears a little bit. We're going to do this again. More molecular orbital diagrams. But this time we're going to start talking about a different kind of bond. Go ahead, Margo.
So are both of these wave functions for one T2 valid? Because we wrote 2
No.
different ones.
So the one that I wrote out before is incorrect. And jeez. The one I wrote before is incorrect. So it cannot be, right? Basically, this is some sort of summation of these guys, and it's supposed to be representative of all possible MOs. So this is incorrect. Just going to cross this out. Each one, so there's going to be multiple degeneracies here, right? Because in addition to the PX and the DYZ, you're going to have PY and DXZ. And you're going to have PZ and DXY. I got ahead of myself. Okay, whoops. So now I want to start talking about other kinds of bonds. So normal covalent bonds are familiar. And you have a metal and a hydrogen. And people tend to think about normal covalent bonds of this type as sort of being, or you can think about dissociating them in this fashion. This is considered homolytic cleavage. Right? So this is normal for CH bonds. It's sort of typical to think about them in this fashion. And you imagine when you make something like this that the metal and the hydrogen each bring up an electron to make the bond. So typical of organic compounds. But in transition metals, another type of cleavage that people think about is this kind. What is that one called?
Heterolytic?
That's heterolytic cleavage. Now, why do people think about this type in transition metals? It's an electronegativity issue, right? So you've got titanium, extremely electropositive, gives up its electrons to the hydrogen. You can think about the hydrogen as a hydride. So people talk about titanium H4 as they name it titanium tetrahydride. Okay, and that's sort of a statement that the electrons are really on the hydrogens. In general, we're going to talk about transition metal complexes in this way. The metal is plus, the ligand is minus. But it is not a fair description of many transition metal complexes. When you make your diagrams and stuff, we're going to rely on this concept. It is not an accurate description of many compounds. Okay, but we're going to talk about it this way to make our lives easy. And you will see why that is the case. All right. There's another class here, in addition to normal covalent. What's the other one? Dative bonding. Dative bonds, that's where one partner brings up 2 electrons. And the classic example is this metal ammonia complex. And we have to put some formal charges here, right? you're gonna have 4 bonds to nitrogen, you better have a positive formal charge on it, because it's like ammonium. 3 bonds to nitrogen is ammonia, 4 bonds to nitrogen is ammonium. So when you have 4 bonds, you better get a plus charge. Associating this, of course, is heterolytic. We don't tend to think about dissociating nitrogen without its electrons, okay? So we're going to make a lot of molecular orbital diagrams that have these kinds of descriptors in them. The big bonds. So, and you're going to draw a lot of transition metal complexes with dative bonds. Inorganic chemists, for instance, look at compounds like this one here. This is cobalt hexamine 3+. Now, what's missing? Formal charges, right? You gotta have a plus, you gotta have a plus, you gotta have a plus, plus, plus. What's the charge on cobalt? Why 3 minus and not 6 minus? You have to balance the charge out here. 3 minus. Nobody writes it this way. Why not?
Weird seeing electrons on a metal.
It's just weird to see all those charges all over the place. It's a kind of a mess, right? So in our class and in general, in the literature, what you're going to see is this. And in fact, people will sometimes write this. Those of you, well, now that you've done your Lewis math structures very carefully, very rigorously, you know there are formal charges missing over there. Okay, so we're going to just put that aside for a second and go ahead with that picture in our mind. This is going to cause confusion later that we're ignoring them, but beware. All right, so let's take a look at an ML representation of this kind of thing. So we have sigma donor ligands. And let's take our metal here. Every inorganic chemist's favorite orbital. DZ squared. And we are going to make a bond Ammonia. Now, which orbital is this?
That's,
I like your answer. I would say it's an sp hybrid. Has a lot of s character. So it's probably not exactly sp3. More s than sp3. Okay. It's a hybrid orbital. We don't need to worry too much about exactly how it's composed. We're just going to think about it kind of like a hydrogen 1s orbital. Okay. You can treat it that way to make your life easy. So let's take a dz squared here, and we're going to combine it with this ammonia lone pair. And we'll have the dz squared empty in this example, and these guys make a bond like that. Now this is the sigma orbital, and this is the sigma star, and there's sigmas because there's no shared node, right? All right, so this sort of thing works regardless of whatever your donor is. It could be, you know, a phosphine, it could be hydride, it could be methide. It's just a lone pair. Now let's think about, sorry, I forgot my electrons here. Let's think about what this means, okay, for the metal and for the ligand. We're going to talk about this MO like it's a ligand orbital. And we're going to talk about this MO like it's a transition metal orbital. So this MO has a lot of dz squared character. This MO has a lot of lone pair character. It's not really a lone pair anymore. It's part of a bond, but it's like the nitrogen lone pair. Okay. So if you talk about it in that way, what happened to the nitrogen lone pair on making the bond? It went down in energy. Why did it go down in energy? What's that?
You're mixing the orbital mixing. So when you mix orbitals of similar different energies, you will split the orbitals, and those that are lower in energy will be lower or to stabilize the bonding, and the anti-bonding becomes higher in energy.
Yeah.
It's supposed to go down even more.
Yeah, when you interfere the two, you get a constructive interference and a destructive interference, and the constructive interference is lower than the starting. Let's use electrostatic language, okay? This is a very important way to think about this stuff. Give me an electrostatic description of what happened here. Just plus likes minus, plus doesn't like plus. Give me that kind of a description.
We treat the cobalt as 3+ like we wrote there, then when you're putting a negative lone pair closer with a plus charge, I guess it likes that.
Right. Yeah. So this is kind of like an acid-base description, right? Who's the acid in the acid-base description here?
Cobalt.
Cobalt. Why is cobalt the acid? It's an acceptor of electrons, right? It's a Lewis acid here. An acid is something that has positive charge. It's an empty orbital. It's an acceptor of electron density. It's hungry for electrons. Ammonia will burn you because it's a base. It uses its lone pair to donate electrons to acids, right? You could have H plus and NH3. H plus is definitely the acid, you know that. It's the acceptor. So here we have an empty dz squared orbital that is accepting electron density from an ammonia. That lone pair is the base. This dz squared is the acid. This is the source of positive charge. This is the source of negative charge. So what happened to the lone pair on binding the dz squared empty orbital? It went down, and in electrostatic language, it's harder to pull the electron off of it now. You're stabilizing this electron pair relative to vacuum on binding this positive charge. Duh. You guys got to be good at this. And I noticed that like about a third to a half over many, many years, this is like a thing that hasn't quite registered yet. This electron pair is ionizable. You can rip electrons off of it, but you got to pay a penalty. When you stick a positive charge onto that electron pair, it gets harder. Right? This is just a plus minus game. You add a plus charge, electrons go down. It gets harder to pull the electrons off. This is an acid, this is a base. Okay? You can describe all these interactions in that way. Now let's do that again in a somewhat more complicated manner. High donor ligands. Typically, you get one sigma bond and two or one pi bonds to go along with it. Okay. Classic example. An amido ligand. There's your sigma. Where's the pi? Add our lone pair of nitrogen here. Now it just sort of looks like an ammonia molecule, although I made it flat in this drawing. So this is like an sp2 hybridized one. This electron pair is a donor. We know that. You can think about it donating to the metal. And then you can write a different resonance form like this. Made a pi bond. The second bond is a pi bond using that electron pair. Just like ammonia borane, where the ammonia comes along, gives its electron pair to the empty orbital on the boron. Bring up with the plus charge. You've got 4 bonds to nitrogen. 4 bonds to nitrogen is like ammonium. And you made a plus charge. You better make a negative charge. If you start at neutral, you better end neutral. All right. So how does this work? Well, let's draw our metal. We have our easy square. We've got our hybrid orbital here on NR2. In this case, since it's planar, it's kind of like an sp2 orbital. There's your sigma bond. The lone pair of pi symmetry is going to be in a p orbital. How about the orbital on the metal? Which orbital can make a pi bond with this p orbital? What was that? All right, dxy is a good answer. Is there another one? It depends upon where you rate the axes, okay? But a d orbital is one answer. Metals have p orbitals too. So you could draw a p orbital here on the metal and make a pi bond that kind of looks like ethylene. Or a d orbital. There's your pi bond. So you can have the sigma orbital square, you can have the pi orbital. If if this is gonna be the z-axis now, since we labeled this dz squared, this thing better have z in it. We'll call the plane of the board x. Now, in this picture, we're gonna consider both of these guys empty. Okay? Why both empty? Well, it's like nr2 minus, but the electrons on the nr2 thing donating to an empty orbital on the metal. We can think about this lone pair donating to an empty orbital on the metal. Here, we've got pure p orbital for making the pi bond, and this guy is going to be x in our example. And this guy is going to be an sp2 hybrid, making the sigma bond. Okay. All right. So in general, when we draw these things out, what we're thinking here is M nr2 minus I'm going to say it again and again, metal plus, ligand minus. That is going to be our default description. It's not a fair representation of all molecules, but it is going to be our default description. All right, so let's write out the orbital interaction diagram. I'm going to do this using a lot of board space here. On the left, I'm going to write something called the sigma only picture. And on the right, I'm going to write the sigma plus pi picture. What I'm going to do here is combine some d orbitals with some p orbital or with the nr2 fragment. So I'm going to pick two starting orbitals that look like this. We're going to have an sp2 hybrid of sigma symmetry. We're going to have a pure p of pi symmetry. In our picture, where we have nr2 2 minus, we're going to put 4 electrons in here. So I'm going to give this guy a minus charge up there. In fact, I'll put pairs in there to make that clear. All right, you might say, wait a minute, why are we doing this? So nitrogen's got 3p, 3 equivalent to 2p orbitals and an s orbital. That's true, but we're going to represent this fragment in this way. We're going to pre-hybridize and define our orbital basis set in this fashion. You could pick whatever you want. If you want to start with 3 p's or 3 2p orbitals and 1 2s orbital, you can, but that's sort of complicated. I'm going to pick the MO diagram of nr2 as my starting point, and I'm only representing lone pairs, because that's all I really care about. The rest of it's going to be spectating for our purposes. Okay, so you get to define your starting point. Why did I split them in energy this way?
Is it because hybrid orbitals are more stable relative to like pure orbitals occupied by like their own lone pair?
That is a part of the answer, yes. When you mix S with P, it drops in energy because S is lower than P. When you mix P with S goes up in energy. Ionization energy difference is what defines these two. You put a little S in there, it drops it relative to pure P. All right, so let's take those two. And now we're going to mix them with some 5 d orbitals over here. We've got a dz squared, we got a dx squared minus y squared, dxy, and dyz, dxd orbital. Now, this is the sigma only picture, so I'm only going to draw orbital interactions for the sigma one. Forget about the pi's here. So we're going to have one interaction with dz squared up there, with this orbital down here to form a sigma bond as star. And because I'm not considering pi bonding, I'm going to write this pure p pi symmetry lone pair. That I'm going to take the rest of these guys, 1, 2, 3, 4 orbitals here, just like that. And I'm going to say these are non-bonding. Okay. And just like before, this filled orbital down here, what kind of character would you say it has? It's sigma symmetry, but think about the components that make up this molecular orbital. How would you best describe this MO? It's like the lone pair of nitrogen, right? It's ligand-like. Okay, so if you were to write out a symmetry adapted linear combination, it might look something like this. Bonding combination of these two, where this coefficient is large. Okay, and how about this one? Same story, but reverse, right? This is kind of like the d orbital rather than the ligand orbital. And so this guy is going to look a lot like a dz squared. And that NR2 coefficient is going to be small. There'll be a node, of course, because it's an antibond orbital. So this MO is very dz squared like. This MO is very NR2 like. That's a consequence of where they start on the diagram. Splitting the energy difference between these guys gives rise to this kind of thing. Now, let's do the sigma plus pi picture. Again, we're going to start with our 5 d orbitals. Okay, and now we're going to make bonds. We already know about this one here. We got our sigma, our sigma star. And what happens to the pi bond? We're going to have pi this time. We'll make another bond, right? This is the pi bonding. This is pi anti-bonding. Now notice something up here. These two did not end up at the same energy. Why is that? No, these are all the same. These are two different energies, that's true.
Pi orbitals, like, they don't overlap as well as like sigma bonding orbitals.
That's the answer. If we used your explanation here, this guy is further, it would not split as much. The big difference here is sigma and pi. Sigma bonding is better than pi bonding. More important. It really is. You know, you have large splittings associated with sigma and smaller splittings associated with pi. And that's kind of why we do this. Okay, there's multiple reasons, but people often only talk about the sigma picture, and the pi is like a perturbation on the sigma, because pi bonding is weaker than sigma bonding in most examples. and then we have a couple more. 1, 2, 3 orbitals left. These guys are non-bonding. All right, so let's draw the socks out here for this pi star. What does that pi star orbital look like? The metal, NR2. We're just going to draw the pi symmetry interaction now, not the sigma. What does that look like? Right?
Mainly metallic.
Mainly metallic, that's good. It's closer to the metal, so it's going to have a lot of metal coefficient. What do the orbitals look like?
He's out of phase with the P.
Out of phase because it's pi symmetry orbital. We'll write our p orbital on our nitrogen, pi symmetry. Then we're going to write our d orbital. And it's going to be out of phase. With another coefficient on the metal is larger than on the NR2. Same thing down here, except the other way around. This time, they have the right phase to interact. So this pi, oh, gotta put some electrons in here. The pi and the sigma both drop. This thing looks an awful lot like the lone pair of nitrogen perturbed by the metal. And this makes sense because this electron pair, which is really kind of like the nitrogen lone pair, just made a connection with the loose acid. Metal is empty. So this electron pair dropped. Okay, so sigma is greater than pi, the low-lying orbitals are energy minus. Think about this as an acid-base interaction. However, it is often the case that transition metals have these kinds of pi donor ligands, and the metal also has lone pairs. And that changes the picture. So what happens if the metal center has electrons? All right, so we just did this case where we have an empty transition metal, 1, 2, 3, 4, 5. And you're making a connection to a middle 2 minus. So it's like this. Right, and these two guys go down, and these two guys go up. This sigma 5, non-bonding pi. So this empty transition metal stabilized these 2 electrons. And now let's take a filled transition metal. I put 8 electrons in here. We have a filled NR2 minus. Sigma pi, non-bonding, pi star again, sigma star again. But now we have to add these electrons. And I've chosen 8 electrons. So what happened? Something very different happened. We still drop these in energy. Same story for the NR2 fragment, right? But up here, we pushed electrons up. That's very different. Now, does that make sense to you from an electrostatic perspective? Yeah.
Well, it's like if the transition metal is filled, then it's not as positively charged, and so when you bring the lone pair closer, it doesn't get stabilized, or it might get repelled.
Very good. Okay, so the electrons on the metal mean the metal doesn't act as an acid in the same way. In fact, you have electron-electron repulsion happening here. Let's consider 2 bases for a moment. How many of you are familiar with this example? Comparing a hydrazine and an amine. Hydrazine is used to send spaceships into outer space. And part of the reason is because these 2 lone pairs interact with each other in a repulsive fashion. You have 2 sources of negative charge here, fighting it out. So when you think about pulling an electron off of this amine versus this hydrazine, it's much easier to take an electron off of this molecule because the 2 lone pairs are interacting with each other. You're forcing lots of negative charge on top of lots of negative charge. And that creates a very energetic situation. And I have diagrammed that for you here. Now we have a lone pair on the transition metal and a lone pair in this filled pi symmetry p orbital interacting with each other. This electron pair went up. This one went down. When I think about ripping an electron off of this molecule, it's going to come from here. That's the one that's most easily ionized. So the compound that you form, the electrons go up in energy because of this repulsive Coulombic conundrum it's in. You're forcing 2 electron pairs on top of each other. In MO language, one of them goes up and one of them goes down. And that result is that this is easier to ionize. The electron comes from here. So when you have pi donors, if the metal is an acceptor, meaning no electrons in that pi symmetry orbital, then there's just a stabilization of charge. But when the metal is also a pi donor, you have butting of heads going on. And that will raise the average energy of the electrons. The metal's electrons go up. The ligand's electrons still go down. It's a little bit confusing. But if you just think in terms of electrostatics, it's a little bit easier to remember. Okay. Here, metal doesn't really care. It's just doing its job, stabilizing these electrons. Here, there's a fight going on.
Is the stabilization of the lone pair pi MO the same in both cases?
No, actually, in fact, the interaction strength depends upon the bond length. And so stuff like that will be influenced by many different properties. In fact, when you have an empty metal like this, because there is no repulsive interaction, this NR2 fragment can get closer. When you have a repulsive interaction, it'll actually make the bond longer.
So this item would be 5.
The strength of the interaction will actually be weaker because the bond is going to be longer in the case on the right, for the reasons I just mentioned. And so the splitting will be larger in this case. Also, we haven't talked about this, but if you just have 2 hydrogen 1s orbitals interacting to make a bonding and anti-bonding level, the anti-bonding level is slightly higher and the bonding level is lower. It's sort of asymmetric. Doesn't matter for this case. The important thing, the molecular orbital picture is sometimes best rationalized in light of the electrostatic picture. So you have to learn to think about this in terms of giving electrons and accepting electrons in an acid-based sense. And then trust that picture, because that picture is pretty easy to construct, right? Plus and minus like each other. You can take that picture and hold it in your mind's eye and look at the diagram and say, well, how do I use that to talk about what happened there? That's sort of, that you'll be asked to do that in exams. That's how you want to learn to think about this type of stuff. Or do you have a question?
No, I was just gonna ask, overall, even though the electrons on the metal go up, overall it's more stable than if they weren't bonded, or a bond would be formed, correct?
Well, the bond is formed, I guess is what I would say.
Okay.
And so the compound is stable.
Gotcha. So like the decrease in energy from the ligand is enough to like counteract.
Yeah,
the-
overall, the molecule would rather have that than some other situation than just falling apart.
So like an empty transition, where would you normally find like empty transition metals relative to like filled transition metals? Would filled transition metals be more down in the series, like let's say like a rhodium or an iridium, and like the empty one would probably be like vanadium or
Correct. You got it. That's exactly right. The right-hand side of the transition metal series are kind of like the halogens. And oxygen. The left-hand side is like boron and aluminum, gallium. So you'll find a lot of Nr2 minus and Nr2 minus. There's the 2 minus with 1 R and the 1 minus with 2 R's. You'll find those on the left-hand side. You put those kinds of things on the right-hand side, and you get these filled interactions, and things tend to fall apart.
with rhodium.
Yeah. All right. We'll revisit this when we start next time, and we'll see you guys on Monday.
I'll talk.
Are you doing what?
That's literally covering yeah. Yeah, that's a good question. See the symmetry and then like try to break it down into like what operations.
This is best done over email. There's nothing special happening.
Yeah, it's like organic, it's like where are the what's the pKa and where are the electrons coming?
Usually open.
It's like where can I put like my electrons and like what makes sense? Especially like the symmetry. This is a bit more grounded chemistry, like actual use of catalysts. So like, I understand it, but today's lecture was fun.
Internuclear node.
Oh, yeah.
Yeah.
So like on that, I saw that.
like I don't know, well, I have something that I know, like.
So this is the node in this pi symmetry thing. And this d orbital also is split by that same node. That makes it can't do that with this one. There's a node here. But it doesn't anymore.
Awesome, yeah. So, yeah,
Professor?
Yeah, see you.
Thank you.
You're welcome. How's it going? You're brown bagging it today, huh? Where did you get your tea? Halal food cart. Huh. Uh-huh.
Yesterday, and hung out in with all the grad students and stuff, and I started asking him a lot of questions. What is this, what is that? He started talking to me about quantum dots, and so I went and looked at
Nice.
it.
Your cell phone toothpaste somewhere up there.
I remember you walking out with your cell phone in hand.
You sure it's not in that chair?
No, sir.
Maybe,
I certainly had it, I'm sure I'll find it.
Yeah, I'm pretty sure I saw you holding your cell phone.
I remember it, I remember picking it up, well, I know why I did. They telephoned, well, I'm pretty sure it was the idiots that run the universal connexus. My phone shot. My booster shot.
the room and I'm
The
destroying it.
computer thinks this is about here. I'm gonna guess at the sense it is. But you just walk in up here and they.
Get you. Yeah, I've got to do that too.
There's absolutely no reason they should make you fill out the silly electronic form. Probably to remind you. But I think that's what they did, because it's right.
It's like a lecture. Organic and physical consultants. Yeah, third is typical. We take Argo and Pecan. Sometimes people take it at the same time as they're taking Pecan. Sometimes people take it in their last year after they have Argo and Pecan. Kind of just dividing like the chemistry. Yeah, the chemistry major, you have to have this class. It's a lot of fun. Yeah.
It was like pretty.
Uh-huh. Yeah, they're sort of like talking pieces, you know, most of the discussion is about the properties of molecules, and these are just sort of like in facilitating those kinds of conversations.
So other than like the YouTube videos, do you give out any materials?
No, or is textbook. These are talking.